of substance, okay? Last part of this is that we're going to apply the divergence theorem, okay, from Calc 3, right? So we have the integral over the boundary of our region according to the divergence theorem is equal to the integral over the volume of the divergence of this vector field Q in our volume, okay? So the normal, the dot with the normal here gets translated into the divergence of the vector field itself integrated over the volume, okay? So this implies then that we can write everything under the integral over the volume, okay, by rearranging what we had before and say, well, the integral over this PDE for all V that are subsets of U is equal to 0, okay? Well, if it's true for any possible subset I should like, you can always take those subsets and shrink them to points, okay? And it's not hard to prove then that this formula is just true everywhere, okay? That du dt plus the divergence of the flux, okay, is equal to F, this creation-destruction function, okay? This is the basis of really building up many of the reaction-diffusion equations that you see a lot in physics, biology, chemistry, okay? So a few remarks, okay? First of all, when does this not work? Okay, when can't we have a nice balance law? Well, it doesn't work if functions are not smooth enough, okay? Since we have to swap differentiation and integration, okay? Second of all, what is this function f, okay? Well, it's usually given, okay? So for example, it could be an external source, okay? It could be a reaction term, okay? Or it could be a body force, okay? Okay, what is Q? Well, again, this is our flux through each point. And this is often derived from constitutive laws, okay? So think of like, you know, Newton type laws of motion, okay? And so let's look at an example for concentrations, okay? What we have then is what's called Fick's law, okay? And this just tells us that if I have some concentration of some chemical, okay, it's going to flow down the chemical gradient, okay? Chemicals like to spread out and homogenize in media, typically. all other things being equal. And so they're going to flow from high to low concentration. Okay? And so in this case, this would imply that du dt is equal to k, the divergence of the gradient of u, or just k, the Laplacian acting on u, where k is our diffusion coefficient, and here we're just setting f equivalent to 0. Okay. So you should read section 2.4. Okay. That talks about constitutive laws of traffic flow. Okay. And the model we wrote down before, the Inviscid-Burgers equation, is related. Okay. So they're not always necessarily clean and linear. You can certainly have nonlinear constitutive laws. Okay. The last example I want to discuss before I conclude is that of the mass density of some aerosol, okay, in a fluid. Okay, so let's say we spray perfume or, I don't know, insecticide or something like that into the air. Okay, and there's some flow of that air in some, in some direction. Okay, flowing with some velocity. Okay, C is in RA. Okay, we could think of, dropping some pollutants into a river or something like that. Okay, so what should our Q be in this case? Well, if we just have transport, then without any diffusion, we're going to have that Q is equal to the just velocity of the fluid times U. Okay, so du dt, okay, plus C dotted with delta U is equal to 0. Okay, this is sometimes called pure advection. Okay, just purely advecting or transporting things. Okay, but we're often interested in the case of transport plus diffusion. Okay, so you drop stuff into the river, it spreads out and it gets transported. Okay, well, in this case, Q is equal to C U minus K delta U. And the PDE that we get is going to be du dt plus C dotted with the advection or drift term, okay, plus K delta U or Laplacian of U, okay? And this is what's called the advection diffusion equation, okay? It's broadly applicable in physics and mathematical biology. Think of, organismal populations spreading out based on this, or chemicals spreading out in a fluid, okay? So just to summarize before we wrap up, okay? With balance laws, we really are looking for an equation that describes how the amount of some substance, okay, changes, and this is going to be given by how much substance we have entering, either by chemical reactions or actually just flowing into some domain, minus the rate at which that substance is leaving, okay? And importantly, the PDE derivation, okay, is going to require some smoothness, okay, of solution to apply divergence theorem, okay? So that's it. So just to look back at what we went over in this lecture, okay, we talked about classification of second order PDEs using this principal symbol, okay, that's associated with your left-hand side, computing the discriminant of it, and then looking at where it lies in terms of this partitioning of the space of possible principal symbol values. We showed that wave is canonical hyperbolic, heat is canonical parabolic, elliptic is canonical, canonical elliptic is given by Laplace's equation. And we also looked at balance laws and how to derive them using knowledge of the creation and destruction of some substance and its vector field flow in the medium that you're looking at, okay? And so armed with these tools, we can go forward and know a little bit more about how we arrive at some of the PDs that we're going to look at, how they're classified, and the next step really will be to build up a set of tools for solving them. So next week we'll talk about method of characteristics and really a way of converting a broad class of PDs into a set of ODs that can then be solved in order to find specific solutions to initial and boundary value problems. Okay, so